we're going to turn our attention to a very important concept in chemistry known as classification of matter. You can find this information in section 3.1 of your text in chapter 3. The reason that this is so important is because a simple definition of chemistry is that it is the study of matter and the changes that matter undergoes. So being able to look at matter and classify it by composition, understand what types of matter belong in a certain category and why they belong there, is a very important foundational beginning to a study of chemistry. So we are going to turn our attention to a table known as the classification of matter table. You'll find this table on page 65, figure 3.2, and as I've indicated here, this table needs to be committed to your memory. You need to be able to have it as a tool to examine all of the different types of matter we will be looking at this semester. So let's take a look at the table, and at the top of it, of course, is matter. And in red, I have written a condensed definition of all the terms that you see on the table. So let's take a look at matter and how to define it. It can be defined as anything that has mass and occupies space. But I just want to mention here, that is not the world's best definition. Why? Because in order to really understand this definition, in order to understand matter, you'd have to have an understanding of mass, another technical term we've already used without really defining it. And mass, what is mass? It's a measure of the amount of matter present. So I've not used that definition before. I've just sort of assumed that you had a handle on it, but now we want to unpack it more tightly. So notice our dilemma. To define matter, we use the term mass, anything that has mass and occupies space. But when we go to define mass, what is mass? We turn right around and use the word matter to define it. Mass is a measure of the amount of matter present. So if you don't have a good handle on what matter is or what mass is, you're kind of spinning your wheels here. And that is actually not uncommon in chemistry. As we learn things, it automatically leads us in a path that requires us to learn something else, something more. And in fact, it will be very difficult to have a good understanding of matter without delving into the atomic theory, which is where we're heading to next. The atomic theory helps us understand that all matter is composed of atoms. But more about that later. So here we have matter, and we are taking matter and we are classifying it into two major categories. The first category we call pure substances, and I'm going to use that term again later on, so without having to write it all out, you'll see me just abbreviate it P period S period. Now, what are pure substances? Well, pure substances can be simply described as matter that has a fixed composition, meaning its composition is not changing, it's not changing into some other different type of matter. Its composition as a pure substance is fixed. And we see that pure substances can be further subdivided into two smaller subsets. The subset on the left is elements. And I know you have heard the term elements before. You should be able to name some very common elements that you've encountered prior to enrolling in a chemistry class, like oxygen, like nitrogen, like the metals gold and silver and copper, known as precious metals. So we've heard the term elements before, but now we're going to take a closer look in this class about the atoms that make up elements. So you see that elements are composed of the same type of atoms. That means atoms which have distinct chemical and physical properties different from atoms of other elements. And the periodic table, which we will be looking at often this semester, is an organization, a classification of the different elements that we have identified. And we'll talk more about the periodic table and its organization in the next chapter. Right, so elements composed of the same type of atom which have distinct chemical and physical properties different from atoms of other elements. Now you see here in blue I've thrown in something that doesn't necessarily have to be presented here, but I don't want to forget to present it in another place, so I just kind of anchor it right here. There are certain elements that are always found in nature, chemically bonded together as a group of two atoms. Hence, we call them diatomic elements. They are always found in a packet of two atoms of the same type bonded together. And you are responsible for memorizing that list of diatomic elements. Now, I've presented them here, and I want to give you a shortcut, a mnemonic device, a memory device, to help you remember using the periodic table. But let's just read that list: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. This is the list of diatomic elements that you are responsible for memorizing this semester. Let the periodic table help you with that process. If you look at the periodic table, you'll see that nitrogen, oxygen, and what we call the halogen elements, fluorine, chlorine, bromine, and iodine. These are all diatomic elements, and they form the shape of an upside down L on the periodic table. Right, so this set of elements, diatomic elements, if you look at the periodic table, you see they are arranged in the shape of an inverted or upside down L. So you will have access to a periodic table on a quiz or an exam. It's a very easy memory device. In case you forget, you look at the periodic table and it will remind you, oh, there they are in that inverted, that upside down L format. The only diatomic element that is not part of the upside down or inverted L is hydrogen. And you will see hydrogen, the very upper left corner of the periodic table. It is also a diatomic element. And there are ways to remember hydrogen as well for being in this group. We'll talk about that later. So, elements, one category of pure substances. What is the other category of pure substances? And it's compounds. Now remember, both elements and compounds, fixed composition. So looking at the definition of compound, we see that a compound is two or more elements, as in atoms of two or more different elements, chemically bonded. Now I'm jumping ahead here. I have not yet discussed what a chemical bond is. We'll have a whole chapter on that in Unit 2. But I want your notes right now to incorporate this term, even if it's a little fuzzy to you. As we go through the semester and learn more about bonding, you'll understand. It's sort of like a chemical superglue, so to speak. So compounds, atoms of two or more different elements chemically bonded together in a fixed ratio or fixed composition. And I've put down the formulas of several different examples of compounds that I know you're familiar with, that you've encountered. Everybody's familiar with water, and pretty much everybody knows its chemical formula before they even take a chemistry class, H2O. So notice atoms of two different elements in this example, two hydrogen atoms chemically bonded to one oxygen atom, always in that fixed composition, fixed ratio. The next example is carbon dioxide, CO2. The next example, sodium chloride, using the chemical symbols for the elements sodium and chlorine in a fixed ratio, 1 sodium present for every 1 chlorine, NaCl. And then the last example, Fe2, Fe, the symbol for the element iron, right? Fe2O3, this is otherwise known as rust. What happens when you put a metal nail outside? The nail is primarily the element iron. It reacts with oxygen in the atmosphere and forms this compound, Fe2O3, its chemical formula, fixed composition, which we call rust. Before I move to the right side of this table, let me just mention here that compounds can be separated into the elements that make them up. But in order to do that separation, you have to carry out what we call a chemical reaction. You can't use a physical process. You have to do a chemical reaction, otherwise known as a chemical change, in order to take a compound and separate it into the elements that make it up. You cannot accomplish that through any physical change. You have to do a chemical change to do that. And a chemical change is also known as a chemical reaction. More about that in the next video. So we've talked about pure substances with fixed composition. Let's move to the other major category of matter. Definitely a category that has more examples that we can point to in nature, and that is the category known as mixtures. So how can we define mixtures? Mixtures are two or more pure substances, physically combined but not chemically bonded together. So they're physically mixed, they're in the presence of each other, but they are not chemically bonded together. Therefore, it's very easy to change the composition of any mixture. Just add more of one pure substance or more of another pure substance. You change the ratio, you change the composition. Examples of mixtures that you're very familiar with is air. The room that I'm doing this presentation in has air present in it, or I certainly wouldn't be alive. I can't see it, but I can feel it moving through my nostrils when I breathe in. Air is a mixture of two primary gases, nitrogen and oxygen, both, of course, these diatomic elements that we mentioned earlier, as well as small amounts of other gases that are also present in air, like carbon dioxide, like helium, like neon, and the rest of the noble gases, which you will become more familiar with. So air, right? Two or more pure substances, in this instance elements by and large, physically combined but not chemically bonded. All mixtures have a variable composition, which is the hallmark difference between mixtures and pure substances. Pure substances have fixed composition, mixtures have variable composition. You can take mixtures and separate them into the pure substances that make them up. This separation can happen through physical changes because the components, the pure substances of a mixture, are just physically combined, not chemically bonded. So you can separate the pure substances that make up a mixture into the individual separate pure substances that are the components through physical changes. Again, you are familiar with the list of physical changes I am listing. All these separations take advantage of some property that's different with the pure substances that are physically combined together. There's something different about a property of those substances that you can use for the separation. Here's the first physical change I've listed: filtration. Everybody's familiar with a coffee filter and know that the purpose of the coffee filter is to take the coffee mixture and separate the liquid component from the coffee grinds that no one wants to drink. The grinds have larger particle size and get trapped in the filter paper. The liquid coffee mixture just seeps right through the tiny little holes in the filter paper. So filtration takes advantage of the differences in particle size present in the components of a mixture. Distillation, a fancy term, sometimes abbreviated just still, use a still, takes advantages of differences in boiling points of substances. And when you do a distillation, you heat a mixture of pure substances, which have different boiling points, and the one that has the lowest boiling point, in other words, it becomes a gas most easily, will boil out of the mixture, become a gas, and separate away. So distillation takes advantage of differences in boiling point. Extraction. Extraction, if you've done laundry, then you understand extraction. Extraction takes advantages of solubility differences in order to be able to separate components. So the material of the clothes does not dissolve in water, but if you put a little soap in the water, you can extract out the oils and grease and dirt that are attached to the clothes and dissolve them into the water and remove them in the process of washing. So extraction, you separate pure substances from each other as a result of solubility differences. Centrifugation is a process where you separate substances based on density differences. And we just looked at density in chapter 2. So a centrifuge is an instrument that spins very rapidly, and it will take a mixture, and as it spins very rapidly, the more dense substances in the mixture will be pulled to the bottom of the container, and the less dense substances will be on top. Usually centrifuges are used to pull solids down to the bottom of the container because they typically are more dense, and leave the liquid component of the mixture on top, which is typically less dense. So all of these physical changes, one more time, are taking advantage of differences in physical properties of the pure substances that are combined together in the mixture. Mixtures can be further subdivided into two smaller groups: homogeneous mixtures, which are also known as solutions. All solutions are homogeneous mixtures. Homogeneous mixtures are characterized by having a uniform distribution of components. When you look at a homogeneous mixture, the mixture looks the same all throughout. And the reason that it looks the same is because a dissolving process has happened, where one or more components are dissolved, one or more pure substances are dissolved in another pure substance. So it gives that uniform distribution. A very common example of a homogeneous mixture or a solution is Kool-Aid, the child drink, where you basically take water and dissolve sugar in it. So it's a sugar water solution. And then to make it more interesting, you add some color to it, maybe a little bit of flavoring to give it a bit of a zip taste. But when you look at the Kool-Aid mixture, it looks uniform throughout. Its composition, though, is still variable. All you need to do is add a little more water, stir it, and you've diluted the Kool-Aid so it is less concentrated. Or you could add a little more sugar, stir it until the sugar dissolves, and then you've made the Kool-Aid sweeter, right? So composition can vary, but the dissolving process achieves this uniform distribution. Here's one other example of a homogeneous mixture that I want to mention. It's called an alloy. And this is a term that many times students have not encountered prior to some sort of introductory chemistry class where we formally look at it. An alloy is a mixture of two or more different metals, and you mix them together until you have a uniform distribution. And you may wonder, well, how is that possible? Because we know just from experience that metals are solid, right? So how do you get this uniform distribution if you just have these different solid chunks and you physically put them in contact with each other? How do you get this uniform distribution of metals in the mixture? And the answer is, well, that has to be achieved by dissolving. So you have to heat that mixture of metals up until you melt them all. And then in the liquid state, you can dissolve this mixture of metals together. Then cool it down and allow it to harden and solidify. And what you have is an alloy. It is a homogeneous mixture of metals achieved by a dissolving process through heating. So alloys, an example of a homogeneous mixture. The last type of mixture category that I would like to look at with you is a heterogeneous mixture. And the first key descriptor of a heterogeneous mixture is that it has a non-uniform distribution. Unlike homogeneous mixtures, non-uniform, meaning you look at a heterogeneous mixture, you see different substances present with boundaries separating them. You can clearly see boundaries or even different phases present. If you've ever scooped up sand and salt water, there's a heterogeneous mixture. The sand in the bottom of the container and then the salt water, seawater above it, you see a boundary or a phase separating them. So heterogeneous mixtures have distinct boundaries that separate the components of the mixture. And there are many, many examples of heterogeneous mixtures, but I've chosen one of my personal favorites, and that's a chocolate chip cookie. I love chocolate chip cookies. And if I get to choose a chocolate chip cookie from a batch, of course my eye is looking for the chocolate chip cookie that has the greatest number of chocolate chips embedded in it. And I can see those chocolate chips. They have a different color and a different composition than the cookie dough part. And there are phases, boundaries, better term, separating the chocolate chip part from the cookie part. So heterogeneous mixtures, non-uniform distribution, of course, also variable, and distinct boundaries, in some instance just plain distinct physical phases of matter separating the components of the mixture. The last thing I'd like to do is give an example using this ring that I have just taken off as an example of how you classify matter according to this table using this ring, right? If you can see the ring clearly, and I hope it's showing up, it looks like it has a metal band that looks like some sort of a 14 karat, 18 karat gold, right? Fine jewelry composition, and then stones that are present in it as well. And these stones are diamonds. Small diamonds, but diamonds nonetheless. So how would we classify this entire ring? If you have it in your hand, what does the entire ring, right? Where does it fit on the classification table? And I hope that it's as clear to you as it is to me that this is an example of a heterogeneous mixture. I clearly see the gemstones, the diamonds that are present with a distinct boundary separating the diamonds from the ring, the metal ring itself. So the entire ring is a heterogeneous mixture. Now, what if I was able to yank the diamonds out and just have the diamonds in my hand? How would we classify diamonds themselves on the periodic table? And some of you may know that diamonds are a form of the element carbon. One of the ways that you find it in nature as a solid is in the form of diamond, the element carbon. Actually, and unfortunately, not the most common way that you encounter the element carbon. The most common way you encounter the element carbon, I'm trying to point to the tip of this pencil, which needs sharpening. The most common form of the element carbon is graphite, right? So pencil lead is an example of the element carbon, but so is diamond. So diamonds would fall under the element category, pure substance, specifically atoms of the element carbon. What about the metal band that makes the ring up? How would you classify that? And I told you that it's probably 14 karat gold or 18 karat gold. Pure gold is 24 karat. And this ring is not pure gold. I can tell by the color. It's not this kind of brighter yellow color associated with pure gold. It is also harder than pure gold is. Pure gold is a softer metal. So this is not pure gold. What is it? It's a mixture of basically two elements, gold and silver. Mostly gold, but with some silver mixed with it. If you sample every portion of the ring and analyze it, it has the same mass percent of gold to silver in its composition. So it's a mixture with a uniform distribution. That means it must fall under the homogeneous mixture category, and it's an alloy. So once again, the entire ring is a heterogeneous mixture. The diamonds that are present in the ring are an example of an element, and the metal band is an example of a homogeneous mixture, an alloy of two precious metals, gold and silver.